Okay, so 5.3 is about the definite integral, and this is what we're going to spend the bulk of the rest of the term looking at. So it's good to really kind of get our heads around this. So the integral or the definite integral, this is the integral sign, just like you would see d dx as a derivative sign, plus as an addition sign, subtraction. This is a operator. It tells us we're doing something. So this says we're taking the integral or antiderivative of the function f of x with respect to the variable x. That's what this dx is really telling us. It's like, if you think back to the little approximating rectangles, this is a little delta x. Now, just like we had a bound where we were looking for the area or approximating area underneath the curve from A to B, where AB is a closed integral. This is the lower limit down here, just like it is with the sum. This is the upper limit. So we're taking the integral, the definite integral, we're finding the area underneath the curve f of x between A and B. So that's really what we're doing in 5.3. Now, 5.3, we're defining this integral to be the limit as n goes to infinity of the Riemann sum. This right here, f of a plus k times b minus a over n. This is the height of an approximating rectangle. This is the width of an approximating rectangle. We're doing n rectangles, but then we're taking the limit as n goes to infinity. So we have an infinite amount of rectangles underneath the function right here. So we're getting the true area when we do this. So a couple rules and a couple theorems. Um, if f is continuous on the interval ab, then the integral exists, and f is integrable over ab. So basically what we're saying is that the amount of area underneath the curve exists as long as the function is continuous on that little closed interval from a to b. Other things we have is this. Now notice, if we're taking the integral from a to b, that's how we say this, of f of x dx, that is going to be the opposite of taking the integral from b to a. So if we change the bounds of integration, that's going to change a negative sign out there. This is saying the amount of area from x equals a to x equals a equals 0, which that should make sense because there's no area underneath a point. An infinite amount of points, different story. Now, because this is a limit, the integral, the definite integral is defined to be a limit and a sum, which are both linear operators, and they respect addition, subtraction, constants, etc., etc., etc. The same rules apply that do with limit laws and sum laws. So this k times a function, the k can be pulled through. This is what this rule is saying. The integral from a to b of f of x plus g of x is the integral of f of x plus the integral of g of x. The integral of f of x minus g of x is the integral of f of x minus g of x. That's it. Now, this next thing is saying that the integral, the actual area underneath this curve, f of x, is somewhere below the maximum value of f of x times the width of this total interval. So it's somewhere above the minimum height times the interval, and it's somewhere below the maximum y value times the integral, which that's not a big thing at all. Now, if f is greater than g, that is the y values of f are larger than the y value of g on some interval ab, then the amount of area underneath f is going to be larger than the amount of area underneath g. And if f of x is greater than 0 on ab, then, and we're saying that f of x is greater than 0, meaning all the y values are above the x-axis, excuse me, then the integral, the amount of area under the curve between a and b is going to be greater than 0. Last thing kind of falls back into 5.1 with the average value. So if y equals f of x is non-negative and integrable over ab, then the area under the curve AB equals this. The area is the definite integral because it has bounds. Indefinite integrals don't have bounds. So the definite integral of f of x between a and b. The average value is going to be that area divided by the total width of the interval we're looking at. So, other things we have is this. The notation n goes to infinity also means the double bars is a width. It's called a metric, but it's telling us that the width of a partition goes to 0. Same thing. So as the number of approximating rectangles goes to infinity, the width of each of those rectangles goes to 0. Just some notation that we might be using. Now, for the examples. We're assuming a couple things. Oh, express the limit as a definite integral. So here, if we're expressing the integral, or the limit as a definite integral, the limit is p, the partition width goes to 0, the sum of 1 over ck times delta ck, p equaling 1 to 4. So our partition is going from 1 to 4. Those are giving us our bounds of integration. 1 over ck is giving us our 1 over x. Delta xk is giving us our little dx. That's all that's doing right there. Now, here we're supposing that the integral from 1 to 9 of f of x dx is -1, meaning the amount of area underneath the curve between 1 and 9 of this function f of x is -1, which that can make sense. That just means that we have that the function is below. So once again, this integral from 1 to 9 of f of x dx is -1, meaning the area underneath this curve equals -1. It has to be below the x-axis for that to happen. The integral from 7 to 9 of f of x dx equals 5, and the integral from 7 to 9 of h of x dx equals 4. So this is just talking about the area underneath these curves. So if we have the integral from 7 to 9 of f plus h, the sum of these two functions dx, well, we can take the area of the individual function f and h individually. We see that this area is 5, this area is 4, 5 plus 4 is in fact 1. Now, the integral from 9 to 1, well, we don't know what that is exactly. We have the integral from 1 to 9, but remember, the rule told us that we can flip the bounds of integration and we make this negative. So as we flip these bounds of integration, we make this integral negative. Negative integral from 1 to 9 of f of x dx is just -1, which gives us 1. In the area underneath the curve between h of x and f of x, that's what this is really saying right here. Well, we have from 9 to 7. We don't know what it is. We're looking at 7 to 9 here, 7 to 9 here. So first of all, we have to flip these and make a negative. That's what we're doing right here. Second thing we have to do is kind of distribute that negative through. When we do that, this negative goes to the f, making it positive, so that's positive. The negative goes to the h, making that negative. That's what we have right here. We split this integral up to the integral of f minus the integral of h. That's 5 minus 4. That's going to give us 1. Now here we want to find the area by graphing in geometry. So if we're looking at the function 1 minus the absolute value of x, well, the absolute value of x is a v. It goes up. That negative reflects it, and 1 moves it up 1. So that's what we're looking at right here. Now, the bounds of integration says we're looking at this between -1 and 1. So -1 up to 1, down to 1. So we're looking at this area underneath here. Well, this has a width of 2, a height of 1. 1/2 base times height is the area of a triangle. 1/2 times 2 times 1, that gives us 1. That is the area underneath there. Now, if we think about this function y equals x, it's just a straight line. And we know because y equals x, this ordered pair, if at the x values b, the y values b. So here, the area from 0 to b would be 1/2 length times width, or height times width. So b times b is b squared. 1/2 of that is b squared over 2. So the integral of x is b, from 0 to b would be b squared over 2. Now the integral from a to b of x would be 0. The integral from 0 to b minus the integral from 0 to a. So that's giving us this right here. Now, if we have x squared, we could do a little bit more, but we're just going to define this to be the definite integral from a to b of x squared is going to be b squared, or b cubed over 3, the upper limit cubed over 3, minus the lower limit or bound cubed over 3. So we're finding the integral from a to, or 0 to 1/2 of t squared. Well, we know this is going to be the upper bound cube minus the lower bound cube, and those are both over 3. So here we have b cubed minus a cubed, both of those over 3. This is 1/2, we plug it in here. This is 0, we plug it in here. 1/2 cubed is 1/8. 1/8 times the reciprocal of 3, which is 1/3, going to give us 1/24. Now, if we have the integral from 3 to 0 of 2z squared, or 2z minus 3 dz, we're going to use some integral rules, split this thing up like we have here. The 2 could actually come through. Because we're going from 0 to 3, we plug the upper bound in here, the lower bound in here. Z is going to give us 0 squared, the upper bound squared over 2, minus the lower bound squared over 2, minus. This is just the constant function 1. So that's like 0 times 3 times -3 right there. Right here, when we calculate this out, we have -9 plus 9, 0 area under this curve, which means that basically somewhere between 0 and 3, it's under the x-axis, it's over the x-axis, and then that's about it. Now, if we're going to find the average value over the interval, if we have this function right here, x squared minus 1 on the interval from 0 to the square root of 3, the average value is going to be 1 over b minus a, the length of this, times the actual area. So 1 over b minus a, 1 over radical 3 minus 0 is just 1 over radical 3. Now, finding the area underneath this curve from 0 to radical 3 is going to be the integral from 0 to radical 3 of x squared minus 1. Split these things up. So the integral of x squared minus the integral of 1. Here, the integral of x squared is x cubed over 1. We plug in our upper bound, we plug in our lower bound. Here, plug in our upper bound, plug in our lower bound, do the calculation, and get 0 again. So that's pretty much it. We'll take it from there in the next class, and we will keep doing some more examples.